today is the most important session for the entire this embedded system design, because today we are going to see the instruction set. So I think for all of you, this is the first time you are going to see the assembly language, or we call it machine language. So it's quite obvious that you do not understand it in the first time. So I request everyone, if you do not understand anything, please on your mic and ask it again and again, because if you don't understand a single thing, then it will be waste of your time and it will be waste of my time. So if there is a single thing, a very small thing which you do not understand, don't hesitate to ask. So please, if there is means there is in a slide you do not understand anything, you can ask me to repeat the slide once again. Okay, so we will start with the ARM instruction set. So in the previous session, I told you, whenever we start with any microprocessor or microcontroller, two things we have to see. First is its architecture. Second is the instruction set. So instruction set is very much important. So today we are going to see the instruction set of ARM. So we are about to delve into a brief discussion about the ARM instruction set. In the upcoming sessions, we will showcase various demonstrations using the ARM-based and Arduino boards, primarily coding in high-level languages. However, in a few lectures, including this one, we will explore the foundational aspects of the ARM processor, focusing on its low-level features. To do this effectively, it's essential to grasp the assembly language features that the ARM architecture offers. In this segment, we will discuss the different types of ARM instructions, focusing specifically on the data processing instructions within the ARM instruction set architecture. Developers working on embedded systems often deal with hardware platforms and microcontroller-based systems, requiring them to create software. While many opt for high-level languages like C, Python, Java, C++, understanding the processor's lower-level features helps making informed decisions about which processor suits a specific application best. That's why we are giving a brief overview of the ARM processor's assembly language features, reflecting its hardware capabilities. Instruction set like ARM can be grouped into categories like data processing, data transfer, and control flow. In the Harvard architecture, we have discussed the von Neumann and Harvard. Can any one of you tell the what is Harvard architecture? Fast, anyone, please. Harvard architecture.
Yeah, Harvard is for means for data storing data they separate, and for instruction there is separate memory.
Yes. So in the Harvard architecture, common in modern microcontrollers, there is a separation between program and data memory. Instructions reside in program memory, while temporary data is stored in data memory. So I think the first year has joined it today. So I'm going to repeat this thing. Whatever the program you write, like you have already written programs in high level languages, it is going to be stored somewhere. What is a program? Program is nothing but instructions. So these instructions are stored in memory, right? So, so this is a memory. Here, the program is going to be stored. Program means instructions. Here one instruction, here one instruction. This is a program. Sorry, a memory. So there are majorly two architecture, Harvard and von Neumann. In von Neumann, the instructions, that is program, and the data, both are stored in a same memory. What is the instruction? What is the data? Can anyone from second year explain? What is the instruction? What is the data? What are these two things? Anyone, please be fast.
Instructions are the command that users or any other person gives, but data that are used
Yes,
in performing some calculations or some reason making.
yes.
The
So
output.
yes, yes, correct. So instruction means suppose I write something, suppose I tell the computer to add two numbers. I give an instruction, add add two numbers. Suppose just I writing 7 and 3. I'm asking the processor to add these two number, add 7 and 3. So this is an instruction which I give to the computer to do something. I tell them to add this number 7 and 3. This is an instruction. Data means certain value. Suppose I write so add R1 comma 3. Now R1 is a register. Register means a memory, a very small memory, which is used to store something temporary, and registers are very fast. They are small memory. So suppose I write add R1 comma 3. That means I am asking to add the value 3 with the value stored in R1. So in R1 certain values are stored. So this is an instruction, means a task which I give the computer to do. While data can be the any value, like so data can be any value like 3, 5, like suppose it's your class and name of all the students in a class. So that is a data. Suppose there is a program to find the average of marks of all the students in your class. So what is the data? Data is name of all the students, marks of all the students. Now you do first, what will do? You will do the sum of everything. So you will give some instruction to the computer to find the sum. So that will be an instruction. Then you will divide by the number of students. Then that will be you get the average. So that is an instruction जो आप कंप्यूटर को देते हो कुछ काम करने के लिए. While data, in the example, what is the data? Data and the marks. So there are two things, data and instruction. In the von Neumann architecture, there is a separate memory for data and separate memory for instruction. While in the Harvard architecture, and Harvard architecture is common in modern microcontrollers. So there is a separation between program and data memory. Instructions reside in program memory, while temporary data is stored in data memory. The program counter keeps track of the address. This is program memory. Program memory means here only instructions will be written. So this is a program memory. Here an instructions will be written, here another instruction will be written, here another instruction, one instructions at in each position. So this have some address. Suppose this have an address 0, 0, 0. This have an address 0, 0, 1. Then the third one will have an address 0, 1, 0. Similarly, every here it has each location has an address. Like it is similar to uh, a house having certain room and each room has a number. So this have an address. So the CPU will execute the instruction whose address is stored in the program counter. So there is a register. There is a register whose name is program counter PC. Program counter. There is a register. What is a register? Register is it is a memory, nothing but memory, but it is small. Small means its size is less. Here this program memory is big because it is containing so many instructions, but the registers are registers are small. Registers are small means it have a small memory, and it is very fast. Fast means storing and retrieving the data from it, it is fast. Means the processor can store the data and retrieve the data very fastly, consuming less time. So these are the registers. So there is one register. Its name is program counter. Here, first the PC will value will be storing 0, 0, 0. So which instruction the processor will execute? The address which is stored in the PC, the corresponding instructions will be executed by the CPU. CPU क्या करेगा? PC में देखेगा प्रोग्राम काउंटर में कि क्या एड्रेस स्टोर है, 000 है. इस एड्रेस पे जो भी इंस्ट्रक्शन लिखा होगा वो वाला, इस एड्रेस पे जो भी लिखा होगा ये वाला इंस्ट्रक्शन, मतलब हमने यहाँ किया सब्ट्रैक्ट R1, R2, तो वो क्या करेगा? R1 में R2 माइनस कर देगा. ठीक, तो वो वाला इंस्ट्रक्शन करेगा. This instruction is executed, the program counter is updated to the address of the next instruction. इसके बाद जो भी इंस्ट्रक्शन लिखा होगा उसका एड्रेस प्रोग्राम काउंटर में आ जाएगा. तो 000 से 001 हो जाएगा. फिर सीपीयू क्या देखेगा? अब ये वाला ये एड्रेस है, इस एड्रेस पे जो इंस्ट्रक्शन होगा वो होगा. सो दैट इज द प्रोग्राम काउंटर. किसी को डाउट प्रोग्राम काउंटर में? So the program counter keeps track of the address of the next instruction in program memory. Whatever the next instruction it is, that address is stored in the program counter, right? Then data processing instruction in ARM involve arithmetic and logic operations on data exclusively using registers. So I have told you, so ARM is nothing but a RISC-based architecture. What is the speciality of RISC-based architecture? They don't deal with the memory. They bring the data from the memory into the register and all the computation happen in the registers. जो भी होना है वो registers में ही होगा. So that is a feature of RISC-based architecture. So the architectures, primarily there are two types. There are many types. Primarily there are two types: CISC and RISC. RISC means reduced instruction set computer, where we are dealing in the, there are many features. One of the feature is we are dealing in the registers, right? So ARM follows the RISC, reduced instruction set computer philosophy, operating solely on register without involving memory directly. So instructions can be of three types, right? One is हम डेटा को ही मैनिपुलेट कर रहे हैं, कुछ ऑपरेशंस कर रहे हैं, ऐड कर रहे हैं, सब्ट्रैक्ट कर रहे हैं. सो डेटा प्रोसेसिंग, राइट? हमारे रजिस्टर में हमने मेमोरी से रजिस्टर में कुछ डेटा लाया, ये एक रजिस्टर. देयर आर मेनी रजिस्टर्स इन माइक्रो कंट्रोलर. देयर आर मेनी रजिस्टर्स, R1, R2, R3. छोटे छोटे मेमोरी सिस्टम होते हैं. अब इसमें कुछ डेटा है, इसमें कुछ डेटा है, इसमें कुछ डेटा है. सो वी आर मैनिपुलेटिंग, डूइंग सम अरिथमेटिक एंड लॉजिकल ऑपरेशंस. सो एक तरह का इंस्ट्रक्शन वो हो जाएगा. We call it data processing. We are processing the data. Second type is we are doing some transfer between the register and memory. One thing, transfer from one register to register is a data processing only. It is not data transfer. Whatever the things we do within the register, that is data processing. So if you are transferring data from one register to another register, that is data processing only. That is not data transfer. Data transfer instructions move the data from registers to the memory, right? So data transfer instructions offer option to move data between registers and the data memory. Control flow instructions change the execution sequence of a program. So I have told you. So this is the this is here. This is the program memory. You can see the ink annotations, right? Whatever I am drawing on the PPT.
Yes.
Okay, so this is the program memory. Here an instruction is there, here another instruction is there. So what is happening? Whatever the next instruction that will be executed, its address is stored in PC. So what is happening? Sequentially these instructions are being executed. But the control flow instructions in the high level languages also you have studied some jumping statements, jumping instructions, we call jumping statements. ऐसा ही कुछ असेंबली में भी होता है। तो हमें क्या है, मतलब 000 से हमें जाना है 000 से हमें जाना है किसी दूसरे इंस्ट्रक्शन पे। सो द प्रोग्राम काउंटर सपोज इज स्टोरिंग 000. After 000 is executed, means the address, the instruction corresponding to this address, the program counter should be 001. But suppose हमारा जो लॉजिक है, our logic of the program make it to go to an instruction 110 because we require it कि इसके बाद ये वाला इंस्ट्रक्शन होना चाहिए, बीच के जो है इंस्ट्रक्शन उन पे नहीं, यहां से यहां आना चाहिए। सो द कंट्रोल फ्लो इंस्ट्रक्शंस हमें क्या देता है कि प्रोग्राम काउंटर पे उस वैल्यू को डालता है जिसको हमको एग्जीक्यूट करना है। सो द प्रोग्राम काउंटर इज अपडेटेड विद द वैल्यू वेयर वी वांट टू गो। So these are the control flow executions. So in the high level languages also we have studied that the any program is normally executed top to right, left to right, left to right, top to bottom, left to right. But there are some instructions like break, continue, go to. These instructions change the order of execution. Similarly, we have control flow instructions which change the execution sequence of a program. So what is happening? The PC points to the ordinarily the PC points to the next instruction for execution, incrementing as instructions execute. However, instructions like jump or subroutine calls disrupt the sequence by redirecting to different address, altering the normal flow of instruction execution. So these are the control flow instructions. So what is happening? The control flow instruction essentially modify the program counter value, changing the normal sequence of instruction execution. So these are the three types of instructions we are going to deal. So is it fine with everyone? So we are going to learn the first type, which is data processing instructions. In ARM instruction set, all registers are 32 bits. See the register I told you, it's a small memory. So in ARM, the size is only 32 bits. Well, 32 bits corresponding to register, it is still big, because if you see the conventional means very old microprocessor, they are 8-bit or 16 bits, 8-bit or 16-bit. Like, but here ARM, all the registers are 32 bits. 32 bits means 4 bytes. So all registers are 32 bits aligned with the processor's ALU capabilities. What is the ALU? Anyone? What is ALU? Second years.
Those which can perform
Which can?
arithmetic operations and logical operations.
Yes. So in a processor, in the processor, we have seen there are many registers. So registers are storing the values, but who is doing the computation? So there is an ALU. ALU is doing all the computation, means arithmetic and logical operations are done by this ALU. Okay, so the ARM processor have an ALU which operate on 32-bit numbers, right? So operations are performed on these 32-bit operands, either on registers or constant, known as literals or immediate values. For instance, adding a constant like 10 to a register involve using such immediate operands directly specified within the instructions. So I told you we can give instructions like add. We are doing adding. So we can do either add R1. R1 means a register R1 with the value stored in R2, and store in either R1 or R2 or any other register. We can store in it. Suppose we are storing the R1 only. So we are adding R1 and R2 and storing the sum in R1. Means R1 means register R1. It has some values like 5. R2 have some value 2. We are storing. This is type of operation, or we can, the operands can be a immediate value, the constant, like we can add R1 with 2. R1 means the value stored in R1. R1 is a register. The value stored is suppose 5. So 5 with 2. Here 2 is not any register. 2 is a constant value. So 5 is added to 2. So these types of operation can be possible either with the values stored in the registers or a constant. But we are not adding with values stored in any memory location. First, we have to bring from the memory to register. This architecture follows it. मेमोरी में हम डील नहीं करेंगे, मेमोरी से डेटा हम लाएंगे रजिस्टर में, वहां पे जो होना होगा रजिस्टर में ही होगा. हम अब दो रजिस्टर में जो वैल्यूज हैं उन पे कुछ कंप्यूटेशन कर सकते हैं और किसी कांस्टेंट या इमीडिएट वैल्यू से भी ऑपरेशंस कर सकते हैं, राइट. सो मोस्ट ऑपरेशन रिजल्ट इन ए 32 बिट आउटकम. एक 32 बिट का नंबर है, दूसरा 32 बिट नंबर है, दोनों को ऐड सब्ट्रैक्ट करो, 32 बिट नंबर का रिजल्ट आता है. So this 32-bit outcome is stored in a specific register we specify in the instructions. So what are the operands and where we are going to store it. However, there is an exception with a special multiply instruction that can provide a 64-bit result. Multiplying two 32-bit numbers can yield a 64-bit product, and there is a multiply instruction version that can store this result across two registers. So all the operations, two registers 32-bit numbers will give a result 32-bit number. But if you multiply a number, two numbers which are 32-bit, the result will be a 64-bit number. It can be 64-bit number. So there are two versions of multiplication in our R. One version will take the most significant 32 bits. Like this is a this, suppose here is the punch 8 bit. So most significant, if I say most significant 4 bit, so these are the most significant 4 bits. Similarly, if there is 64-bit number, what we do, we take the most significant 32 bits, or otherwise what we can do, we can store the 132-bit in one register and another 32-bit in another register. This is a very popular technique of storing large numbers. Like in a, you will also study a certain microprocessor in your course, like 8085, where there is the register size is 8-bit. But if you have to store certain things of 16 bits, we using register pairs, 8-bit storing in one register and another 8-bit storing in another register. So similarly, here in R, we have two versions of multiplication. One version, what we do, we are neglecting the least significant bits. We are taking the 8 most significant bits, 32 most significant bits, and saying that, okay, this is the product. There is another version in which we are storing the 32 bits in one register and another 32 bits in another register. So we have both the versions available in R. Okay, so while we don't delve into instruction encoding specific in these lectures, like how instruction bit correspond to register, we will cover the supported instruction type and their functionalities. So in the data processing instructions, first thing we have the arithmetic instructions. Let's start with arithmetic instructions in R, focusing on addition and subtraction. The basic add instructions like add R0, R1, R2. So this is the code. This is the instruction. So we there are certain codes. So here we have ADD, add. Add means adding the number. Then we specify the operands R0, R1, R2. So this is the assembly language. Okay, specific to R, specific to other processors. Each processor has its instruction set, means how the instruction will be written. Instruction set specify in what fashion instructions are written. And what determines this thing? The architecture. Each processor have different architecture. So the instructions are specific to the particular architecture. So there are different like ARM is there, Motorola is there, then Intel processors are there. So different processors, there are different instructions. In ARM, this is the thing. We have the add, then we have R0, R1, R2. These two are these three are the operands. Add means addition. So what we are doing, we are adding R1 and R2 and storing the sum in R0. So the first operand is the destination register. The other two are the source register. We are adding R1 and R2 and storing the sum in R0. So I think this is the first assembly language code you are seeing. Add R0, R1, R2. Like in high level languages, we have, what is the first program we have seen? Anyone can tell your experience? What is the first program you wrote?
Hello world.
Yes, hello world. So in my ninth class, I have written the first code. It's in Java. So we have written. So this is the, actually for me also, this is the first assembly language code which I have seen. Add R0, R1, R2. But I have seen this thing first in 8085. 8085 is a microprocessor. So there the syntax is a little bit different, but it's fine. So add R0.
तो भैया
Sorry.
ये सेम VLSI में करते थे ना विवाडो में, एंड गेट बनाना है तो आउटपुट फिर दोनों जो बाहर रहता था
हाँ ओके, तो ठीक है। तो जो हम विवाडो में करते हैं, विवाडो इज मोर लोअर लैंग्वेज देन दिस. सो इन इंस्ट्रक्शंस आर, there is a high level languages. Here it is a high level languages like we have Python, Java, C++, जहाँ पे हम we write in a human friendly way. जो इंस्ट्रक्शंस होते हैं वो इंसान को अच्छे से समझ में आते हैं. इससे लोअर होता है हाई लेवल लैंग्वेजेस से. लोअर लैंग्वेज इज द असेंबली लैंग्वेजेस which is, we can read it, the humans can read it, but it is more specific to the hardware. Here this the program which is high level languages, it is not specific to the hardware, but this assembly language is more specific to the hardware. Then we go more lower level of abstraction. Then we will see what we write, or the first years we will learn what we have done in the Vivado, where we are saying the transistors, the gates, the registers, means the circuit. We are playing with the circuit. Whatever the circuit is there, we are playing with it. So that level language is one more level language lower. अब ये अलग अलग level of abstraction क्यों बनाया गया? See, it is very difficult to deal with this Vivado thing. We know, we have learned it. It is a difficult thing. So everyone cannot work in this domain. So what we have different different things. So but जितना हम नीचे जाएंगे level of abstraction में, उतना हम डिटेल में काम करेंगे. So the high level languages is an abstract where we are seeing the things from a programmer view. अंदर सर्किट में क्या है उससे हमें फर्क नहीं पड़ता. Here we are we have wrote certain language like we have wrote in the Python, we write Python code to add two numbers. How the processor is adding two numbers, we don't care, right? We are simply writing a program to add two numbers. We don't care how a processor is going to write. Then we have an assembly languages. Assembly languages is more specific to the hardware. Hardware means the processor. Then we go one more level down. There which we have hardware description languages, where we are saying how the gates, how the transistor, how the basic circuit is working. So these are different level of abstraction. So we have first thing is add R0, R1, R2. We are adding R1, R2 and storing in R0. Then second thing is ADC. ADC means ADC means add with carry. So there is a carry bit. If you have done binary addition, you know it can generate carry bit. So like if you are adding 1, 1 with 1, 0. So this is the binary code for 3, and this is the binary code for 2. If you are adding it, so 1, 0, 1 and 1, 1, 0, and there is a carry 1. So if we use add operation, so we will neglect the carry. But if we write ADC, the carry bit is also added. So ADC means addition with carry. Then we have subtraction. Means R0 equal to R1 minus R2. Then we have SBC. SBC, it is taking care of the carry bit. Means if you write R0, R1, comma R2, so it will do R1 minus R2 plus C minus 1, because we have to whatever the borrow is there, that also we need to consider. Then we have RSB and RSC. So you see the sub operation, we see R0, R1, R2. So R0, R1, R2, if we do sub, so what is happening? We are doing R1 minus R2, but in R, there are certain manipulation that we can do with the second operand, that is R2. There are certain manipulations we have seen in the architecture. We have certain things like a barrel shift. We have barrel shifter. So these are the manipulations that are possible for the second operand. एक तो है कि हम R1 R2 को सीधे सीधे सेपरेट कर रहे हैं, वो बात अलग है, बट आर्म हमको कुछ फ्लेक्सिबिलिटी देता है कि हम दूसरे ऑपरेंड में कुछ और कर सकते हैं, सर्टेन मॉडिफिकेशन वी कैन डू एंड देन डू द ऑपरेशन. सो RSP इज रिवर्स सब्ट्रैक्शन. तो अभी हमको R2 में अगर सब्ट्रैक्शन करना है तो ठीक है, बट हमें मैनिपुलेशन जो है R1 में करना हो कि R1 को हम 2 बिट शिफ्ट करके फिर सब्ट्रैक्ट करें. सो बट द अकॉर्डिंग टू आर्किटेक्चर, here manipulation is not possible. All the manipulations are possible in the second operand. So that's why we use RSB. RSB का use हम इसलिए करते हैं because RSB R0 R1 R2 means R0 equal to R2 minus R1. We will see how we are going to manipulate the second operand. We will see. But for now, just think the thing is, in R there are certain manipulations which are possible in the second operand. So that's why suppose we want to do the manipulations in the first operand itself, what we do, we use RSB, reverse subtraction, in which the first operand is reversed with the first operand. So RSB R0 R1 R2 means R0 equal to R2 minus R1. Similarly, we have reverse subtraction with carry. Here the carry bit is taken care of. So these are the different instructions. The point to be noted is the reason for different subtraction instruction lies in operand flexibility. Having variation like RSB enables subtraction, subtracting a flexible operand from a normal one or vice versa, providing versatility in specifying the second operand. These instructions handle 32-bit numbers, treating them as unsigned or 2's complement sign, which doesn't alter binary addition or subtraction methods. So these are the arithmetic instructions. Then we have bitwise logical operations. ARM offers bitwise logical instructions like AND, OR, exclusive OR, performing operations at the bit level, manipulating specific bits based on operands. Additionally, there is a bit clear instructions abbreviated as BIC. These operations involve adding the complement of R2 with R1, effectively clearing bits in R1 wherever corresponding bits in R2 are set to 1. In a sense, it clears specific bits in R1 based on the ones in R2. Fine. Okay, one thing we can see, there are various simulators are there. So let us see one operations. We can see the add operations. So there are some online simulator possible. So let us see. This is the you can see, right, the window. It's Microsoft Edge, one browser. We have gone to a website, CPU later. You can see it, right? Hello.
Yes.
Yes.
Okay, so you can see this is a simulator. Like we have used walkv for Arduino, so this is a simulator for there are better softwares, but because I wanted an online so that I don't have to download anything, so this is fairly good simulator. ARM. So you can see these are the register R0, R1, R2, R3. These are the register. Then here is the program counter. Initially everything is 0. So what we are going to do, we are manipulating certain values. So suppose these are, you can see kitne digits hai? 4, 8. So but I told you the registers are 32 bits, but here I can see only 8 things. But so how can you justify anyone? What is these things? I told you in ARM, every register is 32 bits. But here I can only see 8 symbols for each registers. Can anyone justify this?
Four register will combine to form.
No. This is this is one register. R0 is one register. It should have 32 bits. But I can see only
MSB.
no. We have done something very similar to this in Arduino when we were doing register level coding in Arduino. We have seen it. Second years, we have seen it. Just can you guess? So the thing is, these are not bits. These are hexadecimal codes. So 0 means 40, 0, 0, 0, 0. By if I write here 1, I wrote here 1. This is not 1 like 1 bit. I'm writing it here. Here we write the program actually, but let's see. So if I write 0, that means 0, 0, 0, 0. If I write 1, what 1 means is 0, 0, 0, 1. If I write here 7, so what will be 7? 0, 1, 1, 1, right? Right? So this is a hexadecimal code. So the binary code is only 0 or 1. In hexadecimal, we have 16 from 0 to 9, then A, B, C, D, E, F. Right? We have 16. 0 to 9, 10 हो गए. उसके बाद से 6 A, B, C, D, E, F. Means if I write F, F means the corresponding binary will be 1, 1, 1, 1. Right? So ये जो है वो hexadecimal में लिखे हुए हैं. So if I do change the value of these registers, we have done some changes. R1, R2 में ये values हमने store करा दी. So this is the program counter which I was talking about. So this is the program counter. So now we are going to write the instructions. You don't have to see this thing. This is for this online simulator. उसके लिए कोड है because इन्होंने किसी जावास्क्रिप्ट या पाइथन या किसी में ये कोड लिखा होगा. So we don't have to just leave it like it. उसके बाद बारे में नहीं सोचना है. So we write our instruction add R0, R1, R2. And so this is one instruction. Let's do one more. Sub. Okay, we are studying the R3. Sub means subtraction, and we are doing R2 minus R1. So sub R2, R1, right? So sub R3, R2, R1 means we are subtracting R2 minus R1, right? Just let's see. You are correct. Yes. So this is the syntax. So this is the, okay. Let's have these two instructions as of now. Then we have compiles. So yes, you can see this is giving a perfect picture. So this is the address. Here is the instruction. Our first instruction is add. What is the address of it? This is the address. Then the next instruction is +4. In ARM, each instructions is if you add 4, you will get the next instruction, right? So this is here. then we do 4 here. You can see the next instruction. All instructions you add 4, you will get the next instruction address. So here is the address. This is the program memory. You can see this is the program memory. So, and this opcode. So what we have here, we have written this in the machine language, which is assembly language. This corresponding corresponding instruction have to uh, converted into certain code. Means a program, your processor will not know ADD these things. So ADD R0 R1 R2, this corresponding the hexadecimal code is this thing. This is the opcode. Okay, you don't have to remember the opcode. So if you do the programming in things like 8085 8086, we have the seed for different instructions. We have the opcode. What is the opcode for this thing? What is the opcode for this thing? So this is the assembly language code, and this is the opcode, and this is the address I was talking about. So the program counter here has, here PC program counter has the value 000000 means this thing. So means this the code will be executed. Add R0 R1 R2. So I execute it, execute one instruction. So you can see R0 has been updated with the value this. If you do the addition of these two things, the R0 have this. You do the addition, you will get this, right? Now the PC value, you can see the PC value has been updated to adding 4. That means this next instruction will be the corresponding instruction which is stored at this instruction, this address. So this sub will be executed. So if I execute one more, you can see R3 value, we will get this, right? So you can do it as your homework. You can just check if you do R2 minus R1, you are getting this thing or not. So here it's getting F. And you see the program counter has been
opcode फिर से बताइए.
Okay, opcode means हमने यहाँ पे एक assembly language code लिखा हुआ है. Add R0 R1 R2. ये हमें समझ में आ रहा है, प्रोग्रामर को समझ में आ रहा है, इंसान को समझ में आ रहा है. बट जो हमारा प्रोसेसर है वो इन चीजों को नहीं समझता, राइट? सो ये चीज इसको हमको एक नंबर्स में करना होगा, बिकॉज ये हेक्साडेसिमल कोड को हम बाइनरी में, द कंप्यूटर्स, ये हम बचपन से देखते आ रहे हैं, कंप्यूटर वर्क्स ऑन 1 एंड 0. तो हमको उस 1 और 0 में लेके जाना होगा. सो फॉर ईच एंड एवरी इंस्ट्रक्शन वी हैव एन ऑपकोड. ऑपकोड हैव मींस इन द फॉर्म ऑफ बाइनरी. तो ये अभी हेक्साडेसिमल में लिखा हुआ है. द हेक्साडेसिमल कैन बी इजीली कन्वर्टेड इनटू बाइनरी, राइट? सो दिस इज द ऑपकोड. यहाँ पे हम सीधे असेंबली लिख रहे हैं. इन मेनी प्रोसेसर्स वी राइट देयर इज ए प्रोग्रामर. वहां पे हमें ऑपकोड लिखना होता है पर्टिकुलर इंस्ट्रक्शन का. तो हमारे पास एक टेबल होता है, तो हम देखते हैं ऐड के लिए ऑपकोड क्या है. ये है, इस रजिस्टर से इस रजिस्टर में वैल्यू ले जानी है. तो उसके लिए ऑपकोड क्या है, ये है. तो वी राइट दैट ऑपकोड, दैट मींस इन द बाइनरी, बिकॉज हमारा जो मशीन है कैन नॉट अंडरस्टैंड दिस थिंग्स, द इंग्लिश एंड इट डज नॉट अंडरस्टैंड दिस थिंग्स. सो दिस इंस्ट्रक्शंस को हम एक बाइनरी फॉर्म में कन्वर्ट करते हैं, which is the opcode. Here it is written in hexadecimal because बाइनरी में लिखते तो बहुत बड़ा हो जाता. That's why we have written in hexadecimal code, right? Okay, so this is, you can do this the CPU later. It says you can write all the instructions, add, sub, and whatever the instructions we are going to learn today, all you can just see. So these are some registers, and this is the program counter I was talking about. So जो दूसरा इंस्ट्रक्शन था ये एग्जीक्यूट होने के बाद द प्रोग्राम काउंटर इज एग्जीक्यूटेड विद दिस, अपडेटेड विद दिस वैल्यू. मींस यहाँ पे अगर हमने कुछ इंस्ट्रक्शन रखा होता तो वो नेक्स्ट एग्जीक्यूट होता. तो दिस इज द प्रोग्राम काउंटर, राइट? So logical operation and R0 R1 comma R2 means R1 and R2. You know, is there anyone who does not know this logical instructions and or? Okay, let's go through it in very fast. And means if you write 0 0 0 and 0 is 0, 0 and 0 is 0, 0 1 and is 0, 1 and 0 is 0, 1 and 1 is 1. So this is the AND operation. Then we have or. Or operation means if there is a 1 in any of the operand, it will be 1. 0 will be if both the operands are 0. So a literal meaning है ना कि and means दोनों true होना चाहिए तभी true होगा. Or means दोनों में से कोई एक भी true हो गया तो true हो जाएगा. Exclusive or means you can see the truth table of exclusive or. Here what we have, if there is a even number of 1, we have 0, otherwise 1. You can see the truth table and you will understand it. Exclusive or. And then we have bit clear, BIC. BIC means R1 and not R2. So what is happening? So suppose the R1 value is 1 1 0 1. We are taking 4 bits. In ARM we have 32 bits. For understanding BIC, let's see. We have 4 bit. This is R1. Then R2 is 0 1 0 1. This is R2. Then when we do not R2, so we have and not. So not is always performed before and. So we perform the not. So not means just flipping the bits. 0 को हम 1 कर देंगे, 1 को 0, 0 को 1 and 1 को 0. This is the complement of R2, not R2. This is R2 का complement, not R2. And then we are ANDing R1 को हम not R2 से AND कर रहे हैं. ठीक है, तो 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0. तो हुआ क्या कि R1 हमारा जो था उसमें वो वाली बिट क्लियर हो गई जहां पे R2 1 था. R2 was 1 at the second position. So ये बिट क्लियर हो गया. And R2 was 1 at the fourth position. ये बिट क्लियर हो गया. बाकी यहाँ पे और यहाँ पे जो R1 में पहले था वही है. So it is clear, the bit clear. So in certain computation we require कि जो सेकेंड ऑपरेशन पे जहां जहां 1 आ रहा है वहां वहां करस्पॉन्डिंगली फर्स्ट ऑपरेंड में वो 0 हो जाए. So let us see the simulation of AND.
Yeah.
हाँ.
What is BIC?
Okay, let's see the simulation of AND. Then I will explain again BIC. Wait.
No,
Let's see
I'm asking the full form.
Oh, BIC is bit clear.
Okay, thank you.
Okay, you understood the means how it is working, right?
Yes, Bhaiya.
Yes, BIC means bit clear. BIT bit clear. Okay, let's see the AND operation. So we can write, here's the editor. So do AND storage is proposed in R4, and we are doing our AND between R0 and R3, and then compile. Then see the program counter is 000. Then we first, then 4 means this instruction will be executed. Okay, then 8 we have this AND operation. Then if you execute, then R4 value will be updated with R4 will be the AND of R0 and R3. R0 and R3, if you do the AND operation, you will get it, this thing. Okay, so this is the, then PC is updated to the next. 8 plus 4, 12. 12 means C. So you can try it, all the operation by yourself. So we have seen the first is data processing instruction. First we have seen the arithmetic instruction. Then we have bitwise logical operations and or means ORR, or exclusive or and bit clear. Then I told you the register move instructions. In the realm of data manipulation, R include register to register move instruction. These are two types: a straightforward move and a move negated operation. Right? We are just moving one register to another, or we can just negate and then move. The move instruction, such as, let's see this operation, we write move R0, R2. That means we are moving the value R2 to R0. This is the instruction move R0, R2. This move instruction is very popular, very common in many of the instruction set. Many of the instructions, so move R0, R2 means we are moving the values from R2 to R0. Let us see. You understand more if you see the working of it here. So let's erase all these things. Right, move R5, comma R0. So the value in R0 will be moved to R5. Right. So the PC is value 0, then you can see the value of R0 is 60, then 11. This is moved into R5. So this is the move instruction, right? Or you can also do what is there? MVN, move negative. Move negative means you can do this thing on your own. Means just taking the complement of the second operand and then moving it to the first operand. Move negated. So the MVN instruction comes in handy for scenarios requiring negated values of 32-bit numbers. Unlike before, these instructions only require two operands. The middle operand R1 isn't necessary here in the encoding. We have R1. Here we have two operands only because we are moving value from one operand to second operand. So here we have only two operands, right? Then we have another type of data processing, which is comparison instructions within the CPSR. So, okay, then see the CPSR. So one register we have seen is program counter. Similarly, we have another register called current program status register. So when we were writing code in higher level languages, like for even number and for prime number, for certain, you are checking whether this number is a palindrome number or not, whether this number is a perfect number or not, magic number or not. In the book, you can see the variable name is flag, right? They use this name flag. Whatever book you follow, they use a variable flag. What was the use of that flag variable? Anyone can tell? Please be fast. We are running out of time. 1 hour is over. Big quick. Anyone can tell what was the use of that flag variable? We were using. Initially, the flag value was 0. Then something happened. We will do our flag equal to 1. Then we check the value of flag.
It will tell whether the instruction completed or not.
So it tells something. Suppose we are playing a game. So there are two houses. I am here at one tower and I send you to search someone in the second tower. I cannot listen you what you are speaking. So I give you a flag. So I told you if you find that person, you just आप क्या करोगे उस फ्लैग को ऐसे ऊपर उठा लेना. You just raise the flag, then I will see. Or if you do not find it, you just keep the flag down. So I will know. So this is an analogy to understand what are these flags. Flag tells us something. So flag means either 0 or 1. The status of that flag tells us something. So here in we have certain flag, like if you do certain computation. So how we will know that number is 0 or not? So there is a 0 flag. So suppose there, right, we had the R1, R2, R1, R2. See, R1, R2 have some values. I do not know what is the value stored in it, right? If we want to see these two numbers are equal or not, what we can do, we just subtract it and see the number is the difference is 0 or not. So what we have some comparison instruction. It compares R1 and R2. So if I write CMP R1 CMP R1 comma R2, it what is basically does, it do R1 minus R2. CMP means compare, and then set or reset certain flags. If R1 minus R2 gives 0, then there is a in the CPSR current program status register, there is a flag. There is, see, this is a 32 bits, right? So one of the bit we call it 0 bit. So it will be either 0 or 1. If this the difference comes 0, then 0 bit will be 1. Otherwise, it will be 0. There are certain bits. So 0 bit, then carry bit. If we are adding two numbers and there is a carry, right? If there is a carry, then carry bit will be 1. So in the CPSR, we have this is this. Suppose here one bit is there, we call is carry bit. Okay, not the particular position is fixed. I'm not. You have to see the diagram. I'm not sure the position means which bit is which one. We can see in the simulator. Right? See. Simulators, it would be there. Yes, you can see here CPSR, current program status register. Here we have the first bit is N, then Z, then C, V, I, S, V, C. These are this. So N is the negative. If the number is negative, then that will be 1. Otherwise, it will be 0. Then second will be Z, 0 bit, then carry bit, then overflow bit, and there are other bits. So these are comparison instructions which are used to do some certain comparisons, right? It is used to do certain comparisons and set the CC, conditional codes. Conditional codes means the content of the CPSR, current program status register. So let us see one, then we will understand better. So what we are doing? We are doing CMP and CMP R0, comma R1. Right? This is the code. We are comparing R0 and R1. Okay. Then you can see here the CPSR value. This is the initial value, right? Then if you do this, you can see what we have done R0 and R1. So R0 and R1, you can see these are not equal. Here it is 1 1 and here is 0 1. So if we subtract it, the difference will not be 0. So you see the 0 bit is not set. You can see here the bit which is set is kind of highlighted. See, the carry bit is highlighted, carry bit is bold. Why? Because what we are doing R0, R1 means R0 minus R1. So, let's see. Yes. So they are doing certain computation and then they are setting this value. So you can see the negative bit is not active, means the difference is not negative and the difference is not 0 either. But let us see if you do, then two registers having the similar value means R0 and R5. And we compare it. Then you can see the 0 bit is set. You see the Z value is kind of, it is dark. And we can see from here the value also 6. 6 means what? 0 1 1 0. So 0 1 1 0. So Z is 1, right? 6 means, if you this is the hexadecimal, if you convert into binary, 6 means 0 1 1 0. So N is 0, then Z is 1. So these are some flags. So comparison operations set the flag accordingly, right? So then we have CMN, compare negated. So what CMN does, it set the conditional code on R1 plus R2. Then we have TST. TST set the codes on R1 and R2. It does the R1 and R2. Whatever the result of R1 and R2, R1 and R2, it set the conditional codes. The 0 register, carry register, negative register, overflow register, or not register, sorry. These are the particular bit of the CPSR, current program status register. And then we can see the values of that CPSR, and then we can know, okay, these numbers, if we which number is bigger, we can do, right? If we just do compare R1 R2, we can see the negative bit if it is negative bit is high, we can tell okay the first number is smaller. These are then test EQ, TEQ. So these are another which set the CC on X1, XOR, X2. So these are doing certain operations, and then setting or resetting. Set means putting the value 1, reset means putting the value 0 on the contents of the CPSR, current program status register. Then I have told you we can specify immediate operands. Immediate operands means the constant values, and here in ARM we specify the constant value with this sign. We call it this hash symbol, means R1 R2. When we write this hash sign, that the ARM will know okay this is a constant. So add R1 R2 and 2 means R1 equal to R2 plus 2. Okay, so this you should do in the simulator and we'll check. So subtract R3 comma R3 comma hash 2. So what you will do, R3 equal to R3 minus 2, subtract, then and. So okay, let's see. Can anyone explain this? The thing is already written, but can you explain this? This and R6 R3, this how it is equal to this? This is a comments. Okay? This is comments. These are comments. This is the code. So has means immediate values, and means the following number is an hexadecimal number. So 0f means if you do 0f in binary, it will be 0 0 0 0. This means 0, and for f we write 1 1 1 1. This is f. So this is 0. This is f. So if we add R6 with this, 0 and anything will be 0. So the first 4 bits will be 0. 1 and anything is that thing, right? So here the 4 bits of the R6. So that's why we are getting R3 03. 03 means the 0th position, 0th position, first position, second position, third position. We are getting the LS, least significance, 4 bits. So this is certain operations. So and then that I was talking about why we have that another variation of subtraction, because we have certain things like shifted register operations. So we have seen in the architecture we have certain things like barrel shifter which allows shift or rotation. So what we can do, we have add. So we have the and. Yes. We have the add R1. Just wait a minute. So we have add R1, R2, then R2 LSL. Hello, am I audible and can you see the screen?
Yeah, bhaiya.
Okay. Okay, so see. Yes, you can see the comparison instructions. It does certain comparisons we have seen. Then immediate operation we have seen. Then shifted register operands. So what is happening? We write add R1, R2, R2 LSL hash 3 means जो हमारा ये जो ऑपरेंड है यहाँ पे थोड़ा सा टाइपिंग मिस्टेक है. R2, R3 होगा add R1, R2, R3 LSL hash 3. What means it means we are doing shift operation. Shift operation means shifting it by 3 bits. Shifting it R3 hash 3 means हम उसको left shift कर रहे हैं. 3 हम उसको लेफ्ट शिफ्ट कर रहे हैं. So like suppose if it is 1 0 1 1 4-bit number, and if we are saying shift by 1 LSL, so ये वाला 0 यहाँ जाएगा 0, ये 1 यहाँ जाएगा 1, this 1 will come here 1, and here it will be 0. So what is this? This operand left shifted by 1. LSL means logical shift left. So here there is a thing R2 comma R3. Add R1, R2, R3, LSL has 3, means R3 shifted by 3, and then we are doing this addition. So these are certain flexibility we have with the second operand. We can shift certain things. So these are very much important. Like you have seen in the second years, what we have, the convolution. What is convolution? Convolution means we are shifting, multiplying, then adding. You have seen the convolution in the which course? Many courses you will see in the. Have you heard of this thing, convolution? For EC branch student, I think 4 or 5 courses you will learn the convolution thing. In the network you have studied. Then signal system you have learned. So convolution means we are doing something, we are shifting, multiplying, adding, shifting, multiplying, adding. So these operands help in. Sorry. Yes. So you will learn. So you will learn these things. So हम प्रोसेसर में वो सारे ऑपरेशंस करने होते हैं. So the ARM हमें ये प्रोवाइड करता है फ्लेक्सिबिलिटी we have. So we can shift the second operand. We can do certain manipulation in the second operand and do the operations. So that's why we have told a reverse subtraction, because this flexibility is given to the second operand only. So these are shifter register operand, and there are different types of shift, like logical shift left, logical shift right. Logical shift right means shifting towards right. Then rotate right, what it will do in rotate right? In यहाँ पे हमने 0 ऐड किया है ना, अगर ये rotate left होता तो ये जो 1 है ये आता, यहाँ पे 1 हो जाता, ये rotate होता है. Then we have arithmetic shift left, arithmetic shift right. You can see these things, rotate right extended, where we include the carry flag and do certain rotations. So you can see here. So LSL here, LSL 5 means we are shifting left by 5 bits. So we are shifting by 5 bits here. और क्या हम जो 5 अगर लेफ्ट शिफ्ट कर देंगे तो राइट मोस्ट पोजीशन पे हम 0 ऐड करते हैं. Then LSR means लेफ्ट शिफ्ट राइट, तो 5 बिट हम राइट में शिफ्ट करेंगे, और यहाँ पे लेफ्ट पे अब शिफ्ट कर दिया तो यहाँ पे जगह बचेगी, वहां पे क्या 0 ऐड करेंगे. Then we have ASR, arithmetic shift right. If the operand is positive, so here is arithmetic operation distinguish between the positive and negative. Logical shift left में हम 0 ऐड कर रहे थे, उसमें चाहे positive चाहे negative. In the arithmetic we have, if the operand is positive we are adding 0, if the operand is negative we are adding 1. For the arithmetic shift right, arithmetic shift left is same as logical shift left, no difference. For the arithmetic shift right, there is a difference between arithmetic and logical. Logical shift left is same as arithmetic shift left. Then we have rotate. Rotate means I told you, rotate right means we are rotating toward the right. और तो यहाँ पे लेफ्ट पे जो जगह बच जाएगी वहां पे क्या आएगा, ये वाली वैल्यूज यहाँ पे आएगी. We are rotating. Then we have rotate with extended bit, which is a carry bit. तो रोटेट कर रहे हैं तो, और यहाँ राइट रोटेट करेंगे तो यहाँ पे एक जगह बचेगी, मीन्स ये वाली वैल्यू ऐसे एक एक बिट इधर खिसकेगी. एक जगह ये क्या आएगी, जो इसका कैरी बिट है वो यहाँ पे आएगा, और ये वाला बिट कैरी पोजीशन पे चला जाएगा. So these are some rotations. Then we have multiplication instructions. If we write mul R1, R2, R3, what it will do? It will do R2 and multiply with R3 and take the 32 bits only. So there is another version which we are using to store the entire 64 bits. We are not going to cover those things, not necessary at this level. So R2 multiply R2 by R3 and takes the rightmost 32 bits and storing it in R1. So I was telling about the convolution. So for that convolution we have something like MLA. I've told you, right, convolution, this is very much important. In the digital signal processing, we have certain things like DSP, digital signal processors, where these instructions are very much helpful. So what we have, MLA, multiply and accumulate, R1, R2, R3, R4. So what is happening? R1 equal to R2 into R3 plus R4, multiplying this number and then adding with this number. So these are the operations which are helpful in digital signal processing. So multiplying the second and third operand, adding the fourth operand, and then storing this first operand. Okay, so for today, I think this is more than enough. The data processing instruction. So this is the part 1 of instruction set. There is 2 more parts: data transfer instructions and the conditionals. So that we will do in the instruction set part 2 and instruction set part 3.